Hello and welcome to The Router, the official podcast of the UQ Computing Society, where we explore the human side of tech. I'm your host Matt, and today we have an exciting episode at the intersection of computer science and mathematics. Burton and Rhuaidi Burke from the School of Mathematics and Physics at UQ both work in the field of computational topology. They're here to give a brief introduction to the field as well as some of the unique challenges that arise when writing software for mathematicians. All right, hello, welcome to The Router. Rhuaidi and Ben, how are you today?
I'm good, thanks.
Grand, how are you?
Grand, wonderful. Okay, I think it would be good to start by asking you both a little bit about your background and what you're currently doing.
Yep, sure. So my name's Ben. My pronouns are he, him, his. I'm a professor in mathematics, but what I do is halfway between maths and computer science, and a lot of it's on computational topology. So this is basically untangling knots with supercomputers, more or less.
Cool.
And I'm Rhodey. I'm a PhD student working with Ben, and I guess I mainly focus on weird and wacky shapes in 4 dimensions, and seeing what we can understand about such things with computers, I think, is probably the gist of it.
Okay. Yeah, so I guess a lot of the audience might not be super familiar with what is involved with weird and wacky shapes on computers. So if you had a few minutes to explain to a first year computer science or first year math student what you're working on, how would you do that?
Sure.
Like, what would you say?
Well, I suppose if you think, I guess, how do I usually phrase these things? If you think about how the surface of the Earth, right, is, curved, and if you wanted to pinpoint, right, a location on the Earth, you could specify, if you felt like it, a longitude and a latitude, right? And that would sort of give you somehow that can give you any point on the surface of the Earth. And or similarly, like if you draw, say, a wiggly, curvy line on a piece of paper, then you could number the points on that, and that would tell you just where any point on that curve was. And there's nothing stopping us then from generalizing this, right? So even with the Earth example, say we wanted to go and have a cup of coffee later, right? You would need to tell me, right? So in theory, you could tell me a latitude and a longitude, right? But maybe we're going to some super fashionable cafe that's, on the 30th story of some new building, right? And so now you have to give me a third number. You have to tell me that it's on the 30th floor. So now somehow we're dealing with a 3-dimensional. If you wanted to plot that event, it's now become 3-dimensional because you need 3 numbers. But then even that's not enough, right? Because what happens if I rock up at, 12 p.m. and you rock up at, 3 p.m., right? We miss each other. So actually you need to also specify a 4th number, right? You need to specify time. So now if you wanted to plot that event, it's now become a 4-dimensional thing. So, this is all, but if we abstract all this away, basically I deal with things that sort of need 4 dimensions in order to, if you wanted to visualize or understand these objects. And so somehow, I suppose with the stuff that I work on in particular, 4 dimensions is where things become very unlike what you might be used to in 1, 2, or 3 dimensions, right? You start getting behavior that you don't see in lower dimensions. And the maths behind all that gets very hard, to say the least. And so somehow, if you're like me, right, and maybe you need you need a bit of a helping hand, maybe, right? You sort of cross your fingers and maybe you think, well, computers are good at sometimes doing hard problems. Maybe I can somehow get the computer to help me with these sort of difficult problems. Yeah, I mean, I don't know if that's terribly illuminating, but
Yeah, that's
something.
no,
of
that's
that
good.
effect.
Okay, so you kind of deal with these objects that are a bit hard to represent or visualize on a computer in some way, and computers, I guess, are the solution to some of your problems. So this all gets worked into, I believe, this project called Regina, which Ben has been leading for some time, I guess. But the project's a bit more than that, right? It has some other tools as well, right? I guess, could you elaborate about what is involved in this big project? And maybe let's introduce, yeah.
Yeah, so it's somehow, I mean, so Regina is a piece of software that does all sorts of things in low-dimensional topology. So when I say low-dimensional topology, maybe I step back. So low-dimensional topology, this includes the four-dimensional stuff that Rhody's thinking about, the three-dimensional stuff, which I spend more of my time thinking about because I can actually see it, thinking about knots. So it's all different kinds of geometry, but what connects them all is that in topology, you don't care about angles or distances. What you care about is large-scale structure. So the classical thing is that somehow a football is the same as a sphere, is the same as a lump of Play-Doh, because you could take one of them and mold them into the other without cutting and gluing. But they're not the same as a donut, because you'd have to punch a hole through the sphere to make a donut, right? Or you'd have to glue up the hole inside the donut to make it a sphere. So there's some large-scale structure that's different between the donut and the sphere, but the same with the sphere and the other things. So topology is looking at that kind of difference, which means in topology, you don't have to care about these kind of infinitesimally intricate sort of curves and surfaces and whatnot. You just need to remember sort of this thing's got a hole, this thing hasn't got a hole, which means you can represent it in a nice discrete way, which is suitable for computers, right? So Regina is a piece of software that deals with three-dimensional topology, four-dimensional topology, knot theory, as in KNOT, knot theory. And it's one of these things that started off trying to implement a handful of very specific algorithms 20 plus years ago. And it just accumulated more and more stuff until it got to the point where it had enough small little things that you could actually glue them together and solve big problems. And so now it's become a much more general toolkit for solving problems in low-dimensional topology because it has enough of these primitive pieces that you can actually do interesting things. So it's kind of, in a way, it's like Mathematica for topologists, right? Except it's not. And I have my own issues with Mathematica, and I haven't touched it for 10 years for good reason, but that's another story. Yeah.
Okay. One thing I'm curious about, because it's something that I've always been a bit puzzled by, is when you have these weird three-dimensional, four-dimensional objects, what data structure do you use to describe mathematical objects on a computer? Like, is there like a specific kind of structure you go to?
So I can give you my answer to this, right? Which is that, so I'm afraid of floating point numbers, right? So, and this probably dates back to when I was doing competitive programming, and you'd have to write a piece of code that solves a problem, and your output was compared bit for bit against the judge's output, which meant you had to have exactly the precise correct answer, and there had to be only one precise correct answer, which is perfectly fine for discrete problems like graph theory and combinatorics, and it's terrible for floating point. So what does this mean? It means that you represent them using discrete structures, which you can describe precisely. So think of, as an example, think of a knot. All right, a knot by a knot. What I mean is, think of a curve going through space, but you glue the ends together. So then you're getting an electrical extension cable, right, which has got an end with points coming out and an end with holes coming in. So you take this electrical extension cable, wrap it up, and then stick the two ends together.
When you put your back in the day when people had wired earphones and you'd put them in your pocket and they'd get tangled up, and then you tied the ends together, or tying a knot in your shoelaces and tying the ends together.
Yeah.
Or a pretzel.
Yeah, you're eating me now. But so once you glue the ends together, the question becomes, can you untangle this knot without pulling apart the two ends, right? Without essentially cutting the string. And the way you'd represent this in a computer is not using sort of a smooth curve through three-dimensional space, but what you do is you try and think of photographing the cable. So you photograph the cable, and then on the picture, what you've just got is strands that go back and forth around the page, and some of them go over each other and some of them go under each other. Right? But at the end of the day, all you really care about is these crossings, these points where one strand goes over another. So if you've got, say, 10 crossings, you have a list of 10 objects, and each of those crossings has 2 edges going out and 2 edges coming from underneath. And you say, well, the upper edge going this way connects to that crossing in this edge, and the lower edge going out that way connects to that crossing at that edge. And so suddenly all you've got is you've got 10 arrays of size 4, and each of those array elements is pointing to one of the other array elements. So you're basically taking the 4n ends of these crossings and pairing them off. And this is something that's, to a computer, has no geometry at all. It's just combinatorics, essentially. It's just some simple discrete structure.
Do mathematicians usually ever aim to try to, I guess, translate from, because you're writing it in this language that's easy to understand if you're tracing through, like, you have your orientations and your crossings and all that, so you can kind of sketch it. But is it ever an aim to try to visualize those knots in any way? How can one do that? Is it a difficult task?
So there's a whole discipline of computer science called graph drawing, which is based on the idea of, here's the combinatorics of a graph, put it on a 2-dimensional page in a way that it's readable, right? And what do you mean by readable? You mean that sort of crossings aren't bunched too close together. You mean that when edges come out of crossings, they don't have too small angles between them, so you can clearly see what's going in which direction. You don't want some enormous areas and some other kind of very squished up areas, but really trying to pin down what you even mean by a nice diagram is a hard question, right? Even deciding what it is you're aiming for is hard, and the graph drawing experts know much more about this than I do. I only go in one direction. Someone gives me a diagram, I turn it into combinatorics, and I never go back.
Yeah.
I don't know. Rodi might have different answers to this, but
yeah, I'm curious about what Rodi thinks, because you're working in four dimensions, right?
Yeah. Well, I mean, especially with the stuff I look at, which somehow starts also somehow involved with knots and turning something that's originally like a one-dimensional knot into a somehow that thing represents a four-dimensional object also in some way. Well, if you're asking though, as far as being able to, you give me combinatorics and I give you a picture back, there's algorithms to kind of do this. Certainly a certain way of encoding knots is called a Gauss code, and various flavors of Gauss code. And there is a way of, given a Gauss code, you can basically go back the other way. So given this combinatorial encoding, go back the other way and basically construct these various types of graphs, and you perform various operations on these graphs, and at the end you get something which looks more or less like a diagram of the knot, which is represented by that combinatorial encoding.
But yeah, I guess the key thing is that it's very discrete. It's never really some sort of continuous representation.
Yeah, it's basically it's quite interesting, because the one that I'm thinking of, at least, yeah, what comes out is it's I mean, depending on how you draw it, it's basically just a glorified graph, right? So I guess this still comes back to then the problem of can you draw the graph nicely?
There's a second answer to this, which is if you live in the world of three-dimensional topology. So when I say three-dimensional topology, so two-dimensional topology is looking at things like spheres and donuts, because you're really looking at the surface of a sphere or the surface of a donut, which is a two-dimensional thing. Think of a sphere as like a beach ball, right? It's two-dimensional plastic blown up. So three-dimensional topology would be looking at things like the surface of a four-dimensional sphere. So these are objects which you build not from sort of little squares or triangles glued together to go around a sphere, but it's built out of little tetrahedra glued together to fill up some three-dimensional space. So there's this magnificent work that, amongst other people, William Thurston was pioneering sort of some decades ago, and there were Fields medals, I think plural, have been won for this kind of study. And what Thurston's big insight was that the topology, which somehow throws away lengths and angles and all of this geometric data, the geometry and the topology are actually quite closely tied together for many kinds of spaces. And so there's these spaces called hyperbolic spaces, which are both very difficult to deal with and also very common, right? Sort of very, very common once your spaces get more and more involved. And one of the best ways to understand what's going on with one of these spaces is to take the discrete data and try and fit some geometry onto it, some actual lengths and angles and so on. And basically what happens is I give you the tetrahedra and the ways that they're all glued together. And this is like your crossings and the ways they're all attached together. It's just combinatorial. Yeah. And from those gluings, you get a set of nonlinear equations. And if you can solve that set of nonlinear equations over the complex numbers, then the solutions essentially tell you where the geodesics, which is the fancy word for essentially straight lines, where the straight lines flow through the tetrahedra, where the flat planes flow through the tetrahedra, how the angles sit within the tetrahedra, which means you can then actually try and draw the tetrahedra in some three-dimensional space and see how the space behaves. And there are people who have software that does this. There's a piece of software called Snappy. And one of the things it does is it solves these equations, and then it will actually let you fly through the space like you're playing a computer game, right? You can sort of zoom through and see what's around you and kind of get a sense of the geometry that you're living within. And that, crucially, that tells you things about the topology, about the large scale structure, which is kind of amazing. But yeah, so this visualization sometimes is quite important.
Yeah, but it's a very difficult problem, it seems, to get your head around and to solve.
Yeah.
I would love to write a similar piece of software one day that does this for the four-dimensional objects that I was talking about, but that's probably
it's like a first-person shooter around.
Yeah. But probably a ways off or
whatever.
So the way the three-dimensional stuff works, right? Because you're a three-dimensional space, you can't just sit back and look at it. Because think of being a two-dimensional person. If you're a two-dimensional person, you can't see a torus, right? You need 3 dimensions to put the torus in. If you're living inside the torus, there are some things you can see, right? If you're living inside a sphere as a two-dimensional person, if you look in any direction, then once you go all the way around the sphere, you see your own butt, yeah? So, and no matter where you turn, you look forwards, and in exactly the same distance, which is one loop of the sphere, you see your own butt, yeah? So somehow, if you're living on a sphere, the world is full of your butt, right? So, yeah. So on a torus, it's not the same. On a torus, if you kind of sit on the edge of a donut, if you think about looking around the kind of the like where you would slice the donut if you wanted to slice it in pieces to give to people, right? Not that you'd want to do that to a donut, but
it's too small. Yeah.
If you look in that direction, then you see your butt really close, right? If you look at the long way around the donut, then you see your butt much further away. If you pick a diagonal and kind of look around that diagonal, then maybe it sort of loops many times around the donut before you get back to yourself. So you're a long way away. And if you pick an irrational slope, then it loops forever and never comes back to you. So you never see yourself at all. Yeah. So
do you wait? Sorry, I just clarify this visualization here. So do you mean like, let's say you have a cross section and you're looking at the donut from above, right? And you have the outer edge of the donut and the inner edge of the donut. Are you talking about the lines tangent to the outer edge of the donut and that straight line as you traverse it and the amount of... am I thinking correctly?
Well, yeah, so that's one loop that sort of does a simple loop around the outside of the hole and comes back to you. You can also just kind of do a belt, right? So without going around the hole, you just go around the dough, yeah? And that's a much smaller loop that comes back to you. But then you could try and do both at the same time. So you kind of go around the perimeter, but at the same time you're going down and then underneath and then up inside the hole and then back outside again. So that's what I mean by a diagonal. But if you pick the slope a little bit wrong, you don't quite meet up. You have to go around again, and maybe again and again and again and again. And if the slope is irrational, forever. Yeah. And so then the way that you can show off flying through a donut to a two-dimensional person is basically showing them this visual field of kind of seeing themselves close, far away, yeah? And kind of seeing how all the copies of yourself move around as you move through the donut. And that gives you some sense of the geometry. So that's exactly what the software does in 3 dimensions. It lets you fly through it and you can see the repeating pictures of yourself and of the kind of nearby structures sort of repeating infinitely often further back. And so you can get this sense of how the repetitions work and sort of what, that's it's a podcast, but Rhodey's drawn a picture, and I'm sorry to all the listeners who can't see it.
So it is just it's a torus with a, hang on, I would describe it to the viewer, a torus with the cross-sectional, yeah, and then you have a trace just over like the cross-section going through the donut as if you're like first person traveling through the middle of the donut and going around. And
maybe this is why you need video podcasts after this.
Yeah, maybe we'll bring video.
Pacman's on a torus. Do people still play Pacman?
It's been a few years. But I mean, I think Pacman's still a pretty common staple in people's, I don't know, phones or an arcade, I guess.
Yeah, so Pacman is exactly on a torus, right? If you go off the left-hand side of the screen, you appear on the right. If you go up the top of the screen, you appear on the bottom. Yeah, and think of left to right as going around the outside of the hole, and top to bottom is just going around the little loop around the dough, right? And then what do I mean by diagonal? I mean going at 45 degrees, and you come back. If you go at 30 degrees, you have to go a few times before you come back. If you go at an irrational slope, you'll never meet yourself again.
Do you have like a link? I guess you can maybe send. I'll put it in the description for the podcast. We've got this nice little description. We can put all these, I guess, visualizations. Maybe if there's some examples or the software that you're talking about before.
So maybe fly through visualizations, there is a book called The Shape of Space. I think the front cover of the book has one of these pictures on it. It's called The Shape of Space by Jeffrey Weeks. And Jeff Weeks was the person who wrote the first version of Snappy, like in the 1990s. Regina lives online at regina-normal.github.com.
Okay. And I'll make sure to link everything so people can find all those. So I guess the next question is a little bit different. So I have, been, like, writing code for I guess software engineers, or typically when you're writing a software product, it's aimed towards an end user who might, need to do something just for like work purposes or business purposes or something. One thing I'm really curious about is there anything unique about when you're writing software for a mathematician? Is there anything different you kind of need to consider? Like, what are the different priorities? Like, how does one incorporate the software into their workflow? Like, what sort of stack do you use? Like, what are the different things about writing Regina? Like,
I might throw to Rhodey before, because I have opinions on this. So
okay.
I might let Rhodey get a word in before I unleash.
Yeah.
The first thing that springs to my mind in how it's probably different is in terms of licensing, probably, and intellectual property on some level. Because somehow, I guess, in a general software development setting, like, well, as you say, like in an enterprise setting or something like that, then presumably there's at some point, you want to you want to monetize it somehow, or sell it, or it belongs to your employer or something like that. But in the case of writing for mathematicians or writing for academic purposes, then maybe the software you write will never see commercial use, or nothing that is produced by this software will have any commercial value, right? It's purely for academic purposes or something like that, or to aid in research. So, maybe you don't want it to belong to your employer, or you don't want it to have to fall into the same. You get into the whole open source and all that sort of end of things. If you want it to be free to distribute and free to contribute to and that kind of thing. That's probably the.
Is that usually an expectation for, like? Sorry to interrupt, but is that usually like an expectation? Everything, all code written for academic purposes, needs to be open source in some manner?
I don't have enough experience to say necessarily that would be the case for everything, but I think certainly for the sort of stuff that I write, what you would hope that you'd be able to, everyone would be able to use it,
And so certainly in the field of low-dimensional topology, it's an expectation. I mean, not an expectation like people will breathe down your neck, but if you have to,
it'll be bizarre. Yeah.
But But I mean, and also there are other areas like you look at computational algebra, right? Trying to solve problems in group theory using software. So there are open source package like GAP is a big open source package for this sort of thing. Magma, which is a piece of software that comes out of the University of Sydney. So this is paid, and I think it's expensive. Like it's expensive enough that you would try and get it through the university, not sort of go down and buy it yourself, right? I think it's anyway. I won't speculate. So that exists, and it's thriving as far as I'm aware. Also, what I find is if I need to do some computational algebra, I won't use it unless I really, really have to. And one of the reasons is simply because at the last time I tried to use it, which was about 4 years ago, we had exactly one license for exactly one CPU on campus. And I was trying to do stuff on supercomputers running in parallel with hundreds of things at the same time. And I could do that with GAP and I couldn't with Magma because licensing. So, so this is one of many reasons, right? People don't know. This is one of the problems with mathematical software is that it's a problem with software in general, but you have no idea how good the software is going to be for what it is you want to do. And in the world that Rhuaidi and I are living in, and the world I live in mainly is three-dimensional, and you have problems which are almost always at least exponential time, sometimes worse. In theory, they're terrible, and in practice, if you have the right clever heuristics and good implementations, and conscientious sort of programmers who are sort of on the ball, then it can be made much faster in practice. But if you just take an algorithm out of a paper or out of a book and hack up the first version you think of, it'll be much, much, much slower. And so if you see a piece of software that solves problem X, you've got no idea whether it's going to be useful until you can actually really experiment with it properly, right? And that's much easier to do if it's open source. And Rhuaidi's dealing with problems, maybe you want to talk about this, but your problems are undecidable, right?
Yeah, well, yeah. It gets worse than exponential in the sense that sometimes for the stuff I look at, there's provably not an algorithm full stop. So
So what's it like writing software for a mathematical audience? And I think one of the answers is it depends on what people are going to do with it. And there are two big things that at least I do with mathematical software. One of them is exploration. So just having a big data set where you can sort of play with lots of things, find conjectures, test conjectures, just see what's going on. And the other is computer proofs, where you actually use machines to do enormous case bashes to produce a theorem at the end. Right? And the algorithm only needs to be run once, and it's to get the proof, and then you have a theorem, and then you don't need to touch it again. So writing for experimentation, this is somehow easier, and there's more and more bits of software coming out in our field for doing this as people start to discover the value of it. And I mean, Rhuaidi was talking about having objects that you can't see, and to me, that's not the biggest problem in our field. It's not that you can't visualize things. It's the fact that if you want to do anything, right? If I give you a triangulated four-dimensional space and I try to do something with it, there are so many details you have to hold on to, right? There's so much bookkeeping that you have to do to be able to sort of trace an algorithm through and solve a problem. Yeah, you want a computer to be able to hang on to all those pieces without making an error, and that's something that's much harder in 4 and 3 dimensions than it is in 2. But then for computer proofs, what you need there absolutely is reliability, and by reliability I mean the software has been coded carefully. It's carefully tested. It's using exact arithmetic. So when I say I'm afraid of floating point numbers, this is also one of them, because I want to produce proofs, right? And sometimes you have to use floating point numbers, and then your proofs have to do things like using error bounds and proving that the error bounds are not sort of are small enough that the solution that you claim is there is somehow not outside them, or whatever, right? So having this sort of fiendish focus on being exact and being precise and being able to trust the result that comes out. This is something that is not always true in commercial software, and it's something that's not always even true in commercial mathematical software. So that's, I think, possibly this is the thing that Regina tries to pay attention to more than anything else is reliable results.
Yeah. And I feel like I feel a lot more people are paying attention to this idea of like formal verification. And just in broadly in computer science, this idea that we need to prove that a program is correct somehow. We need to write our software in a provably correct way. And when it gets to especially mathematical proofs, or especially exhaustive mathematical proofs or proofs that require you checking all the cases, and if checking all the cases like in this certain linear scanning brute force method might be way too slow, so you have to cut it down. But how do you guarantee that cutting down of our search or whatever might not render it correct? Like, how do I guarantee that? So it's a bit interesting to hear about the mathematical perspective of this, because a lot of time in industry, unfortunately, it seems to be the case that people don't consider it to matter too much, especially if the software is kind of like an app on your phone. Like, does it matter? But in this case, it's crucial.
I think it's also like if you're writing timetabling software, for instance, right? What do you want out of it? You want a reasonably good timetable, and if it's not best possible, it's okay, right? Whereas here, you want somehow a certification that this is the best possible timetable, or a certification that there is no possible timetable without clashes, and that's somehow
that can be hard. Yeah. What is your opinion, I guess, on, because I'm not sure if this is the current mathematical. I'm not a mathematician, obviously, but when I heard about the full color theorem, and that was, I think, the first proof that was done on a computer that, like, and it received some negative attention, I guess, for those who might not have wanted to see something proven entirely on a computer. Is that sentiment still present in modern maths? Like, do people have a sort of reluctance to rely on computers for proving?
I think people have. I mean, you will always find different people with different opinions, right? And the way I am seeing it is that the mathematical community as a whole is much more receptive to this sort of thing than they used to be. It also probably depends on the field. So in something like the four-color theorem, I think people think it would be super nice to have a proof that didn't need a computer, and I believe they don't have one yet. But and so maybe they're sort of being able to formally verify the proof is something that you'd want to do. And I think, I mean, I seem to remember hearing about problems involving sphere packing where formal verification was part of the process, I think, and I could be completely off the mark with this. But with low dimensional topology, it's, I mean, like Regina, I would love to be able to formally verify that Regina is correct. And I've been on a mission for the last 6 months to reduce the number of lines of code by modernizing all of the C++ under the hood, and I'm now down to 500,000 lines. So being able to somehow put some formal verification around 500,000 lines of source code is something that I think is going to be somebody else's project.
A big task. I've seen like 20-line, I don't know, procedures that are incredibly difficult to verify formally. So I mean,
and then even, I mean, the software itself, right? There's a ton of code in there, but that code, some of it relies on very deep and very difficult to prove theorems. Right? I think there is at least one point where it relies on the Poincare conjecture, which is no longer conjecture, right? But the Poincare conjecture, which was one of the millennium problems and the only one that's been solved. And I look forward to somebody being able to explain to me how the proof works, because I don't understand it. I'm just trying to plug that into verification software in a way that's not just a black box that says trust the Poincare conjecture. Right? I mean, you're not just trusting somebody's verification process, you're also trusting a human's proof, which has been written in a paper and verified by other humans who are the peer reviewers. And by the way, some mistakes slip through there as well, right? So I think partly also, okay, it's like when I first used to write papers, I remember having a paper which talked about how you could make three-sphere recognition faster, right? This is one of the fundamental problems in three-dimensional topology. And the reviews came back, and one of the reviews said, I see nothing wrong with this algorithm, but why do we care? I don't know of any triangulated three spheres that we don't already, like, I don't know of any problems that we don't know the answer to. right? Like I don't have an input for which we don't already know whether the answer is yes or no. So why do we care about having fast algorithms? And that was not the only review I'd seen with such a sentiment. And by the way, if you're doing 4-dimensional topology, which is what Rhuaidi does, then every single time you do some primitive operation on a triangulated 4-dimensional manifold, you're doing 3-sphere recognition, right? So no, nobody has on their desk a triangulated manifold where you don't know whether or not it's a 3-sphere. But if a computer's going to be doing 4-dimensional code in bulk, it's got to be able to solve this problem all the time, repeatedly in bulk. And exactly is one of the reasons you want this to be fast.
And let me tell you, you need it to be fast.
Yes, I think people, like even some of the people who used to be, why do we care, right? I think they're much more appreciative of this now. And you now start to find people who've never touched computers are now getting very excited because they have just PhD students who can write code, and then suddenly they can do things like the advisors can do things they couldn't do before because they have access to humans who have access to machines, right? So I think people are much more receptive than they used to be.
Do you think that programming skills will become essential for mathematicians, or are they already essential? Do you think?
I think they already are.
Yeah.
Rhuaidi, please.
Definitely. I mean, I think even when I was, first year undergrad, and even in like the what was it? I think it was called Psi 1100. I don't know. It's probably gone through half a dozen different name changes.
Theory and practice in science.
Probably gone through half a dozen different name changes since then. But they always you had to do. Everyone that did a science degree was doing that. Had to do that course, and you had to do a little bit of Python programming each week. And I think even back then, like all not to make gross generalizations or anything, but all the biologists and what have you would go through that kicking and screaming. But then you see so much stuff these days coming out, like in terms of biological research, which is utilizing computer programs, and even in the case of low dimensional topology, like coming back to the knot theory thing, right? Like understanding, how proteins and enzymes and all that sort of thing, as I understand it, are somehow knotted and twisted up, and being able to understand how those objects work and behave. All of a sudden, you do find yourself in either needing computational techniques or computational topology. So. I definitely think I think having exposure to programming the earlier the better, because it'll invariably, like, it's essential, I think.
It'll help. Yeah.
I think one of the things you notice as well, I have long ago lost count of the number of times when I've had someone say, "Oh, Ben, can you code this up for me?" Or, "Ben, do you have an example of something that does this?" Or, "Ben, can you test whether this does blah?" Right? And what you're seeing here is somebody who doesn't know how to code having to find someone they know who A, does know how to code, and B, knows enough of the field to be able to code in that field, and then they have to wait for me to do it, right? And I mean, Rhuaidi knows what I'm like with response time, right? I just, so many people ask me these things, and a fraction of them I actually get done, and I have a whole list of things that I have wish I had time to do that I can't, right? And so what it means is, if you have someone who's trying to do research in the field who will inevitably need to be able to do something on a computer, they have to find someone, ask them, and then sit and wait for that person to get around to it. Yeah. And so it's just much faster if you can pull out a laptop and do it yourself. Yeah. And I think people are also starting to realize this.
Yeah. And one last thing I'm quite curious about with the tech stack for, I guess, programming, because you mentioned things about how, like, speed is really important for your computation sometimes. Is it a tendency for those to write, like, in quote unquote low level languages like C or Fortran, or is it like, do people write in Python? Like, what's common?
You want to go?
Kind of C++ is Regina's language, right?
I think it depends on where. I mean, I found for for me personally, right, it depended on at what stage the project was at, right? Because the software that I write, the very first iteration of it was written, basically it was written in Python. It had some extra bits and pieces floating around, but it was the first version of it was written in Python, just simply because Python is, easy to sketch things in, basically. So it was terribly slow, and probably it was not in, and it was not in any way foolproof. Basically, if you weren't me, it was probably very easy to break it. But then I rewrote that software at the start of this year in C++, and so that's now got the advantage of, well, it's a lot more foolproof, but that's just because of the way I've designed it now. But also, obviously, the speed up, I think, is probably the most noticeable thing. But the point is, though, is that, I think I sketched it up in Python to begin with because it was easy, and then when I needed to move to a lower level language.
Okay, yeah, that makes sense. So that's all the questions I really had. One thing I always ask at the end of these podcasts is, normally if we're talking about some sort of topic, what is a place for those who might be interested in computational topology or that kind of thing? Is there any books that people can read or websites that people can go to, or just software to play around with? I guess I could just tell them to download Regina. But any recommendations?
So there's computational topology, and then there's topology. And I think the problem with computational topology is that it's very difficult to get into if you don't know some topology, right?
Yeah.
So the book I mentioned, The Shape of Space, is a very readable introduction to topology, and it's mainly two-dimensional and then some three-dimensional. It's written at the level for a good high school student to read. So you could take it home, make it bedtime reading, put yourself to sleep with it, whatever. And that at least gives you some of the language to understand what the software is doing. If you downloaded Regina out of the box, you wouldn't know what to do with it, right? And you'd kind of open and close some things and then delete it. Yeah. Snappy has some. Look, I mean, Snappy has some visualization, but it's still, I mean, in some sense, it's the same. You need to know what a three-manifold is. You need to know what. Yeah. Look.
There is. I'm trying to find a link now at the moment. I remember downloading years ago. Somewhere. I'll try and find a link to it. But it was based on The Shape of Space. Where it was certainly very like you didn't need to know what you were doing, right? Because it just had a drop-down menu where you could select different three-manifold or three-dimensional spaces, and it would do this thing that Ben was talking about before, right? Where it, it sort of places you like within that space, and you can fly through it, like flying through a video game or whatever. And from what I can remember, you didn't need to know what was actually going on, but it certainly gave you some interesting pictures to look at.
So Snappy does come with a Python interface these days. So Jeff wrote it in C long ago, and then Nathan Dunford and Mark Culler put together a Python interface around it, and they've been maintaining it for the last decade or so. And so the Python interface is helpful to you. So when you start it up, it says, hello, it's Snappy. Here's some things you can try. And if you just follow your nose, I think it'll at least get you as far as creating a three-dimensional space and being able to play with some of its invariants, in a graphical user interface.
And I guess for those who are more mathematically inclined, let's say they've taken real analysis and maybe some algebra or geometry or something, would you have any recommendations for textbooks or things you might look into, like maybe algebraic topology or something like that?
So the thing with computational topology, the other thing with computational topology is that it means several different things to different people. So there's maybe three big schools of what it means, and one of them is computational low-dimensional topology, like knots and three-dimensional spaces and four-dimensional spaces, which is what we do. One of them is what's called persistent homology. So this is essentially trying to do statistical data analysis using topology as opposed to linear algebra. And there are some things in common, but it's a very different set of skills. It comes much more out of computer science and mathematics. And then there's another flavor of computational topology, which is looking at things like embeddings of graphs in surfaces and this kind of thing, which is really coming out of combinatorics. And so I think this is a correct statement. I think Jeff Erickson, spelled Erickson, Jeff. I think Jeff Erickson has a book, at least he was working on it. I hope it's finished by now, which I believe covers all three. And so that might be a nice introduction to it. Otherwise, for the stuff we do, I think there's not a lot of books.
Is it more like papers and that kind of?
Yeah, look, it's too fast moving. It's too new. So there's papers, there's conferences. So some of this stuff happens at the Symposium on Computational Geometry, which is the flagship CompGeom conference. And the proceedings for those are all online and free to view. It's all open access, and you can kind of see at least what sort of things people are playing with.
All right. Well, I guess I can compile those all up and put them in the description, maybe for those to read, and for the more mathematically oriented, there's some nice links as well. But yeah, thanks so much for taking the time to chat. It's been good to hear about maths and programming and how they can kind of intersect in a way for these specific topology problems. And yeah, thanks so much for your time.
Thanks for having us.
No, it's a pleasure.
All right, that's all we have time for today. Thanks for joining us. As usual, our next episode will be out in a fortnight. Until then, come join us on our Discord community at discord.uqcs.org.